9, 8, 7, 6. We have main engine ignition. 4, 3, 2, 1. And we have solid motor ignition and liftoff. Liftoff of America's Space Shuttle. 7, 6. We have main engine ignition. 4, 3, 2, 1. And we have solid motor ignition and liftoff. Liftoff of America's Space Shuttle on its 4th mission, and we have cleared the tower.
Roll program.
Roger, roll, Columbia.
Houston now controlling. Mission control confirms roll maneuver started. 20 seconds. Thrust looks good. 26 seconds. Roll maneuver completed. 30 seconds. 1 nautical mile in altitude. Throttling engines down to 65% now as programmed. 36 seconds. Plot board status looks good. Mission control. 42 seconds. Columbia now 3 nautical miles in altitude. 46 seconds. Coming up on period of maximum aerodynamic pressure on the vehicle. 52 seconds. Columbia now 4 nautical miles in altitude. 56 seconds. Pass through max Q. Still looking good. Throttling engines.
Columbia, Houston, you
Give
are
it a go.
go and throttle up.
Roger, go and throttle up.
6. We have main engine ignition. 4, 3, 2, 1. And we have solid motor ignition and liftoff. Liftoff of America's Space Shuttle on its 4th mission, and we have cleared the tower.
Roll program.
Roger, roll, Columbia.
Houston now controlling. Mission control confirms roll maneuver started. 20 seconds. Thrust looks good. 26 seconds, roll maneuver completed. 30 seconds, 1 nautical mile in altitude, throttling engines down to 65% now as programmed. 36 seconds, plot board status looks good, mission control. 42 seconds, Columbia now 3 nautical miles in altitude. 46 seconds, coming up on period of maximum aerodynamic pressure on the vehicle. 52 seconds, Columbia now 4 nautical miles in altitude. 56 seconds, pass through max Q, still looking good. Throttling engines.
Columbia, Houston, you
Giving
are
a go
go
at
and
throttle
throttle up.
Roger, go and throttle up.
Mark 1 minute 10 seconds, Columbia now 7 nautical miles in altitude, 4 nautical miles downrange. 1 minute 20 seconds, Columbia now 9 nautical miles in altitude, 6 nautical miles downrange. 1 minute 30 seconds, Columbia now 12 nautical miles in altitude, 9 nautical miles downrange. Velocity now reading 3,900 feet per second. 1 minute 42 seconds, coming up now on negative seats where altitude is too high for ejection seat use.
Columbia, Houston, negative seats.
Roger, negative 6.
1 minute 57 seconds, Columbia now 21 nautical miles in altitude, 21 nautical miles downrange. 2 minutes 3 seconds, standing by for solid rocket booster separation.
Roger, PC 50.
2 minutes 14 seconds, confirm solid rocket booster separation. 2 minutes 20 seconds, onboard guidance is converging as programmed. Columbia is now steering for a precise wind in space. Standing by for solid rocket booster separation.
Roger, PC 50.
8 minutes 40 seconds, confirm shutdown. Columbia returned to space for the 4th time, not yet returned to orbit. Standing by now for external tank separation. Confirm external tank separation. Columbia now moving below and beyond the external tank. Go, no-go status check and mission control by Flight Director Tom Holloway for the first ohms burn and shutting down the auxiliary power units.
Columbia, Houston, your go for nominal ohms 1, APU shutdown on time.
Oh, thank you, David.
Columbia now in proper attitude for the first ohms burn. Prop systems engineer reports ignition on both ohms engine, looks good. Flight dynamics officer Ron Epps reports the following predicted numbers for the first ohms burn. Time of ignition, 10 minutes, 39.3 seconds. Delta V, 153.5 feet per second. Burn duration, 1 minute, 30.5 seconds. A resulting apogee of 130 nautical miles. A resulting perigee of 33.3 nautical miles. At 14 minutes mission elapsed time, this is Shuttle Control Houston. Recovery forces have not been able to locate either of the twin solid rocket boosters or main parachutes. Initial aircraft sightings indicated that one of the boosters had been located resting low in the water, but a report was later received that it apparently sank. Another sighting indicated that the other booster was floating erect in the water, but later reports implied that it too had sunk.
T.K. Mattingly and Henry Hartsfield conducted a thorough evaluation of on-orbit procedures for the upcoming operational era of spaceflight, when Columbia will launch into Earth orbit on a routine basis.
Here's a view taken in orbit as we do one of the ohms burns that I described to you earlier. We did 2 of these burns to get into the 130-mile orbit, 2 more to jack the altitude up to 160, then a 5th one to adjust the entry roll phasing.
Houston, you still there?
Roger, TK, we're here. Your burn looks good.
I was going to say, things look pretty nice here.
The 4,000 ohms burn was performed as planned. Columbia now in a circular orbit at 161 nautical miles.
Experiment Charlie is on. In any event, select Experiment Charlie power off. Verify Experiment Charlie power LED off. Wait 60 seconds and then execute tab Bravo Charlie.
Here's a just brief look at the operation of the continuous flow electrophoresis system. This is a prime example of an experiment or an operation that can only be performed in zero-G efficiently. It must have the space environment. The principle of operation is that biological materials assume their own inherent charge in the presence of an electric field, and that serves as a basis for separating these materials. This can only be done now in the laboratory, and only very small quantities of biological materials that can be used in the treatment of disease can be separated in this fashion. It could be done with a static device, but to increase the yields, you need continuous flow. The principle being to put the biological materials in solution, pass them between the electrodes of an electric field. The molecules with a larger charge would then have the largest lateral displacement in the field as the flow proceeded. Now, the big enemy of doing this on Earth is gravity. Gravity limits how much or how concentrated the solution is with the materials you're trying to separate, because the solution must keep it in, must hold it up, and in gravity, if you get the concentration too high, it won't hold it. Gravity also plays a part in convection. As the fluid is heated by the electric field, convection currents set up, which destroy the purity of the sample being gathered and also affects the quantity that you can separate. In the space environment, you can increase the yields several hundred times over what you can do on Earth. And this is extremely important, because then this allows us to generate clinical quantities rather than just experimental quantities. In the future, we may very well have factories producing biological materials using this same technique. And again, I say the importance is that it can only be done in a space environment where there's no gravity or very little gravity. The device is run, little microcomputer. Here we see the pilot making an input into that computer. The big factor here is the cost. To produce the same amount of material on Earth as we can produce in orbit under a comparable period of time would cost a fortune. So space use of this type of device is going to reduce the cost and make the materials available. This is the first of 6 flights flying this device under a joint agreement between NASA and the contractor. Our first results show that this device worked very well, and the results are very promising.
Results from the prototype's first flight showed that a very thin, yet highly concentrated stream of protein substance on the left was separated from red dye on the right. The thin protein stream, only a portion of which is shown here, is actually over 43 inches long and is 300 to 400 times more concentrated than yields obtained from the same process on Earth.